As can be seen, all of the devices involved in Brayton cycle analysis are steady flow devices that can be analyzed by using steady flow energy equation SFEE. In our analysis later, we are going to neglect the term changes in potential and kinetic energy. Our steady flow energy equation will now become these expressions. Note that the term heat transfer and work will depend on the role or function of that respective devices. Now let's have a look on the method to analyze for each of the devices involved in Brayton cycle. For process 122 across the compressor, since this process runs isentropically, thus we can use the isentropic relations for the ideal gases. This relation can be used to find the specific temperature or pressure. Note that Rp is the pressure ratio P2 over P1 and K is equal to gamma, which is the specific heat ratio Cp over Cv. From the steady flow energy equation SFEE, since the compressor is consuming work and let's assume the process is adiabatic, we can get the expression of power input is equal to the mass flow rate times with the enthalpy at the outlet minus the enthalpy at the inlet, that give us in the unit of kilowatt or kilojoule per second. Since we know that for ideal gases, the enthalpy H is equal to Cp times temperature. Therefore, the SFEE is now becoming this expression. Specifically for our current example, we can have this equation. Process 2 to 3 heat exchanger heat addition at constant pressure. Pressure at state 2 is equal to pressure at state 3. From the steady flow energy equation SFEE, we know that heat exchanger only receive or release heat. For our case, it is heat addition process. Therefore, the term Q dot in is maintained. And there is no work involved in heat exchanger. Thus, our steady flow energy equation will now become this expression. And the enthalpy for ideal gas is equal to Cp times T. Thus, we have this equation. With respect to our example, the equation will be this expression. Note that the temperature at state 3 is the maximum temperature for this cycle. For process 3 to 4 turbine, similar to compressor, turbine also works isentropically. But before that, let's have a look at the pressure ratio Rp introduced previously. Pressure ratio Rp is equal to P2 over P1. We know that pressure at state 3 is equal to pressure at state 2, and pressure at state 1 is equal to the pressure at state 4. So, if we substitute P3 and P4 to the pressure ratio, it will become pressure ratio Rp is equal to P3 over P4. Thus, our isentropic relation for process 3 to 4 will now become this expression. However, this relation is applicable for simple Brayton cycle. From the steady flow energy equation SFEE, since the process is adiabatic and the turbine producing work W out, therefore the steady flow energy equation is now become this expression. For ideal gases, the enthalpy is equal to Cp times T. Thus, or in our case, the equation now can become this expression. For the last process, which is process 4-to-1 constant pressure heat rejection, pressure at state 4 is equal to pressure at state 1. From the steady flow energy equation SFEE, since heat exchanger is not a work-related steady flow devices and it was used to reject heat for this process, therefore the SFEE will become this expression. And if we substitute enthalpy with specific heat at constant pressure Cp times temperature T, since the working fluid is the ideal gases, the final steady flow energy equation will be this expression. With respect to our discussion, the SFEE will be this equation. We also can determine the backwork ratio RBW, which is the ratio between work consumed by the compressor over the work produced by the turbine. In order to determine the thermal efficiency, we are going to divide the power net output with the heat transfer input. Only for simple Brayton cycle, we can use this equation to determine the thermal efficiency. This will be the derivation for this equation for your perusal. The advantages of gas turbine is high power to weight ratio as used in aircraft power plant, quick start operation as in power generation, can be operated on liquid or gaseous fuel, and can be coupled with a vapor power cycle for greater thermal efficiency. And the disadvantages of gas turbine is low thermal efficiency, which led to high operational costs, high startup costs in power generation industry, and high maintenance costs. Our discussion, as for now, only focus on the ideal case, since we assume process through our compressor and turbine is in isentropic process. However, this ideal condition cannot be achieved for the actual operation of the gas turbine engine, since there will be pressure drops across the piping system and across the steady flow devices. One of the factors that led to the situation is the friction, such as between the working fluid with the pipes wall. Irreversibilities across the compressor and turbine. As been discussed in subchapter 3.8, in the actual process, lesser energy is available to do useful work, thus increase the entropy. And heat losses will occur from our system. Although if we try to provide the best insulation or method to prevent heat losses, there will still be heat losses occur. However, the effect of this heat loss might be minimized by providing insulation to our system. Therefore, instead of having constant pressure heat addition and heat rejection, the pressure at the inlet of these processes will be higher than the pressure at the end of these processes. And as mentioned before, the entropy at the outlet of the compressor and the turbine will be larger than the inlet entropy. One of the methods to analyze the actual condition is the isentropic efficiency. Since we have both compressor and turbine in Brayton cycle, thus we might use the isentropic efficiency for the compressor and the turbine. Normally, we are going to use these formulas to find the actual temperature at our device outlet. Meanwhile, if we use the isentropic relationship equation, the temperature that we obtain is the isentropic temperature, T with subscript S.